So hello everybody, first of all, welcome to the third series of intelligent and bio-inspired mechanics, which is hosted by Dr. David River and me in Queen's University, to to make sure everybody know that this is going to be recorded. So in case you don't want to show your face in the recording, please stop your video and also before I introduce our intelligent guest today, Gary, my beautiful friends, I want to make an announcement that for starting next week, our seminar will be moved from 3 p.m. Eastern time, American North American Eastern time to 10 a.m. to accommodate some complaint from both China, Japan, as well as some Europe. They say we are too late. But anyway, with all that being said, let's welcome Gary. So Gary is my wonderful friend. We share the same laboratory building. They are one story above me. I'm in the basement. They are in beautiful the first floor. I'm always jealous. So Gary right now is a postdoc working with Professor Heidi Nepoff in the environmental fluid mechanics lab at MIT. He's also an adjunct professor at University of Amsterdam Lowell. So you can say from his doctoral work and his PhD, his postdoc work, everything about seagrass, from the seagrass fluid mechanics, from seagrass to effect on the environment, also on the nutrition around the seagrass. So I guess without a further amateur introduction from me, so let's give the floor to Gary. Let him to tell us the beautiful seagrass and his passion about seagrass research. Gary, it's yours.
Yeah, thank you, Dixia. It's really nice introduction. So hello everyone. So it's great to be here, and thanks for Dixia for inviting me to this talk. So my topic today is going to be about flow development and sediment deposition along artificial and real seagrass meadows. So since most people are still stuck at home, seagrass might be a little bit far away from our daily life, but the marine environment is out there. I promise you, it's still there, it's beautiful, and seagrass is a very special habitat. So I would like to introduce myself, spend a couple of minutes more. And just in case you spend too much time following the election, the US election news, and missed my bio. So I am a postdoc working with Professor Heidi Nepoff at MIT. And I obtained my PhD there last year. And right now I'm also an adjunct professor at the University of Massachusetts Law. So during my doctoral research, I created artificial versions of seagrass and developed analytical models that predict the motion of individual seagrass blades in waves and currents, as shown by image 1, and also the wave dissipation associated with a submerged seagrass meadow, as shown in image 2, and the evolution of flow velocity and turbulence along a seagrass meadow, an artificial seagrass meadow, and that's image 3. So I used a combination of lab experiments and numerical simulations to validate these models and apply the models to make field scale predictions. So since summer 2019, I have been working in the field to study, the physical mechanisms that impact particle retention in seagrass meadows. And right now, I'm also investigating the impact of artificial structures on the restoration of seagrass. All right, so okay, next page. So here comes the question. So why do we even care about seagrass, and why do we care about protecting and restoring them? So first of all, biodiversity. So they're home to over 100 species. Second, they capture carbon. So which believe that they are over 10 times more efficient than rainforests at capturing carbon. And this is because not just the captured carbon becomes part of the biomass, but also sand settles out and a lot of organic material falls into the meadow and they got stored in the soil. Also, it reduces the energy of waves and currents, and that would stabilize the bed and prevent the coast from erosion. But unfortunately, due to the expansion of human over the past century, we have lost about 30% of the total coverage of seagrass. And the loss continues at a rate of about 1 to 2% or 1 to 3% per year. All right, the next page. So to improve the assessment of these ecosystem services and to provide guidelines for the restoration of seagrass, understanding the hydrodynamics is very important. And the hydrodynamics here, and I'll talk about today, will include flow velocity, the turbulent kinetic energy turbulence, and also sediment deposition. Of course, these three terms are highly related to each other. All right, so here I would like to give an example showing how the three terms flow velocity, turbulence, and sediment deposition are related. So on the right side is an artificial seagrass meadow constructed from plastic blades. So the meadow was deployed underwater for 1 month in, I guess it's from November last year, November to December. So after 1 month, I retrieved this board and found that much more sediment was collected within the meadow compared to the surrounding bare bed. So you can tell there is a really distinct difference. And this is mainly because the flow velocity and the turbulence were lower within the artificial meadow than the outside. And lower turbulence will lead to more deposition of fine particles. All right, so next page. So before jumping into the math and the analytical solution, I would like to introduce the important parameters, including the water depth, capital H, meadow height, H, shoot density, the frontal area per bed area, which is A, which is the product of the shoot density and the width of the blade. And we also consider the flexibility of the seagrass blade and also the size of the meadow. All right, so let's start with the simplest case, which is the submerged meadow of infinite width. So in the lab, this is equivalent to the case where the meadow covers the whole flume width. All right, so I'm just gonna start this video and let's see, where is that button here? Okay, so mute the video and I'm gonna show here. Wait, whoops. Okay. So you can see a vortex structure slowly traveling from the left to the right, right? So, all right, I'll wait until the end of this video. All right, so next page. So here the upper panel shows the velocity profile at the open channel and in the fully developed region. On the right, the profile on the right, on the left is the open channel profile, and on the right is the profile in fully developed region. So here the delta E named the penetration length. Basically, that shows how deep the vortex structure, which is what you just saw. So delta E basically shows how deep the vortex structures could penetrate the metal. And in 2013, Chen et al. Developed a two-layer model to describe the flow development. As you could see in the lower panel, the water column is split into two layers. So the two-layer model assumes that in each layer, the velocity is uniform. So U1x and U2x denote the velocity within and above the metal, respectively, and the subscript F denotes the fully developed region, and U sub infinity is the the depth average velocity in the open channel. Okay, so derived from the continuity equation and the momentum equation in both two layers. So remember the momentum. So in the momentum equation, so two important terms are the drag generated on the artificial plants and also the shear generated at the interface between the metal, but basically the shear generated at the top of the metal because due to the velocity gradient. So derived from these equations, Chen et al. Gave the expression of flow velocity in the fully developed region, U1F. So, and that's, so the ratio of U1F over U infinite is equal to 1 over 1 plus square root of CD. The drag coefficient AH is the dimensionless density of this dimensionless shear density, and divided by 2 times C2 dimensional. So C2 dim hat is a coefficient that describes the efficiency of momentum exchange between the two layers. And that is equal to 0.07 plus minus 0.02 empirically derived times delta E, the penetration length, over capital H, water depth, to the power of 1/3. And of course, this penetration length is limited by the dimension of the metal. So it can't be, so the penetration length, it can be like greater than the height of the metal, right? Because it can't, when you reach the bottom of which the bed, then it's not gonna keep growing anymore, and it won't. It's also limited by how much drag was generated. So, so built on Chen's work, we actually find that an analytical solution existed for the evolution of flow velocity, which is U1x. So the really long equation at the bottom of this slide is the governing equation that could be used to, derive the evolution of flow velocity within the metal. But the analytical solution is kind of complicated, but it does exist, and it's also easily computed by, it could be easily computed by a very simple computational method, like for the other method, because you have this partial derivative, right? You have this partial U over partial X, and that's a function of the velocity itself. All right. So we did lab experiments to validate our analytical solution. So the artificial Seagrass metals here used in our study were constructed from wooden dowels. They're rigid, but I'll talk about the flexible metals later. So for the experimental run I'm going to show for the next several slides. The metal height is 7 centimeter, with the water depth 36 centimeter, and the shear density is 500 per meter squared, and open channel depth average flow velocity is 16 centimeters per second. So we used vectorinos to measure the flow velocity and the TKE, turbulent kinetic energy. All right, so next slide. So the image on this slide shows the evolution of flow velocity along this artificial metal. X-axis denotes the distance from the leading edge of the metal, and Y-axis denotes the vertical position. The black dots show where velocity measurements were taken. So close to the, so from this image, we can observe that close to the leading edge of the metal, so we can see a dramatic change in flow velocity. Due to the drag generated on the artificial planes, flow velocity decreases within the metal, and due to continuity, flow velocity increases above the metal. So at a distance about, let's say 1 meter, around 1 meter from the leading edge, we see that the flow is nearly fully developed, right? And that's basically just the evolution of flow velocity. And then, so from the velocity measurements, we calculated the depth average flow velocity within the metal, U1x. So on this slide, we plotted the measured U1x against the analytical predictions, right? So the triangles with arrow bars are the measurements, and the blue curves denote the model prediction. So basically, we can see that they agree really well, not only in the fully developed region, but also in the developing region, right? So, so that says our analytical model can be just validated using this measurement for these two-dimensional metals. All right, so next page. So as I mentioned earlier, shear is generated at the top of the metal due to the velocity gradient, and the drag is generated on the artificial planes. Also, we call these stems. So considering the energy equation, the turbulence generated by the shear, called shear production, plus the turbulence generated by the drag, called stem production, should be balanced by the energy dissipation. So the shear production hash can be expressed as 1.3 over h times the coefficient C2dim, which is the coefficient of momentum exchange, to the power of 1.5 times the velocity difference cubed. And the stem production is directly associated with the density of the shear density, and it can be expressed as a constant times drag coefficient times stem shear density times the diameter of the dowels times the velocity within the metal cubed. So and basically from that we can estimate, we can calculate the predicted TKE within the canopy, within the metal. All right, so wait, whoops, going too far here. So next page. All right, so so the image on this slide shows the evolution of TKE, turbulent kinetic energy, along the artificial metal. So again, the x-axis denotes the distance from the leading edge of the metal, and the y-axis denotes the vertical position, and the black dots show where velocity measurements were taken. here is the TKE measurements. So what you can immediately see from this image is that there are two hot spots. So really close to the leading edge, you see that turbulence is high, and that's because at that point, the velocity within the metal has not decreased yet. So it's still really close to the open channel velocity, and that's give you higher TKE. However, as the velocity within the metal decreases along the metal, then the stem production, which is the turbulence generated by drag, will decrease, right? And then what you see, the second hotspot on the right, this triangle-shaped basically areas, basically that denotes that basically shows the turbulence due to shear production. So the shear gets higher and higher because the velocity gradient gets higher and higher, right? Because in the open channel, there's no shear. And when the flow develops, the flow above the metal increases while the flow within the metal the flow velocity within the metal decreases. So you have so the velocity gradient gets higher and higher, and you see the shear production gets greater and greater along the length of the metal. So next page. So from the again from this velocity and TKE measurements, we calculated the depth average TKE within the metal. So on this slide, we plotted the measured TKE against the analytical prediction. So the red circles with arrow bars denote the measured values, and the gray shade and the black curve denote the model prediction. So again, again, our analytical model can correctly predict the turbulence as well as the velocity. So wait, oops. Okay, so next page shows again, so we talk about the three terms: flow velocity, turbulence, and sediment deposition, right? So now that our analytical model has been validated, and it shows that we can predict the velocity and the turbulence. So now we want to see if we can actually predict the pattern of sediment deposition. So we did this sediment sediment deposition experiments using model sediment, which is glass spheres. And as you can see on the image on the left, we have these glass slides. We put them on this metal on the board, and we run the flume for several hours, and this glass slide will collect the model sediment. And then after draining the flume and wait until it's dry, we can weigh how much sediment was collected on each slide, right? And then we can say, oh, how much their deposition can be calculated. And on the right, so we plotted this the deposition, it's the milligram per centimeter squared against the distance from the leading edge. So what you can see here is also really interesting. So the horizontal line shows the reference, which is the deposition collected outside the metal. So what you can see from this plot is that really close to the leading edge, you see a lower deposition compared to the reference. And again, that's because the turbulence really close to the leading edge is really high because the velocity is not reduced yet. And the drag generated, the stem production is really high. That's the first hotspot I talked about for the turbulence, the image of the turbulence, right? And also what you can see is that as as the distance from leading edge increases, the deposition first increase and it peaks at about 1 meters from the leading edge, right? And which is exactly around the position where the flow turns into fully developed, right? And then beyond that point, the sediment deposition decreases. And so I think this is because after the flow gets fully developed, the shear will keeps developing, and the shear, and that's also what you see in the plot of the turbulence, right? The shear gets greater and greater, and that's going to drive that's just gonna have a negative impact on sediment deposition, because the shear production will just kick out the sediment, and so you see like a decrease in the sediment deposition beyond the peak. It's beyond the fully developed, where it reached the fully developed state. So and that is the sediment deposition experiments for the 2-dimensional meadows. And again, let's go back a little bit to these the slides where I mentioned about to improve the assessment of these ecosystem services, we need to understand the hydrodynamics, right? So now we already understand that, but we only understand that within or along a 2-dimensional meadow, which is a meadow that covers the whole flume width or the whole flume channel width in the field. And then and also we use this we use the rigid vegetation, right? So what we haven't figured out is what role the blade flexibility and the metal size could play. So, and then I'll talk about that in the next slide. So, so I extend this analytical solution to 3-dimensional meadows, which is the meadow that does not cover the whole channel width. So as you can see on the left, it's basically just like a patch, in this, and this is the cross-sectional, this basically shows the cross-section of the channel. And basically, in this case, the meadow is really just a patch, it's kind of randomly sitting on the bed. And for simplicity, I made this symmetric, but it doesn't have to. So, so the difference here, so difference between the 3-dimensional meadow and the 2-dimensional meadow is that now the shear can be generated on not only the top of the meadow, but also on the sides of the meadow, right? Because you also have a velocity gradient, like sort of like a lateral velocity gradient, and basically for these 3-dimensional meadows, we just say, oh, so in this case, the meadow width should be lower than the channel width, so B should be less than W. And about the flexible meadows, again, so for flexible meadows, we need to add another parameter, which is the deflected height, HD. So right now, because the flexibility of the blades, the blade will bend in response to flow currents. So the height of the meadow will change, right? And in our analytical solution, we can no longer use the original height, H, as the, we can no longer use the original height, H, but instead we need to use the deflected height. So, so the deflected height HD depends on flow velocity and blade properties. It's I'll skip the theories here, but because it's going to make this more complicated. But we do have but theories or models exist that we can use to predict the deflected height just based on the flow velocity and the modulus of the blade and the width, length, with thickness of the blade. All right, so incorporating these two factors into our analytical solution, we end up have so this is the basically this is the analytical solution to the 3D meadows in the fully developed region and in the developing region. So right now we can see here it's similar to the two-dimensional meadows, but right now the coefficient C3dim is the efficiency of momentum exchange between these two layers. We still assume this is two layers, and we still assume the velocity within the meadow is uniform and the velocity outside the meadow is uniform. And we can see here the change is that we use the deflected height instead of the original meadow height h, and we introduce another parameter, which is the channel width and the meadow width W and B. All right, so I'll skip the math because it's just a little bit too complicated. So right now I'm going to talk about the lab experiments that we conducted to validate our analytical solution to flexible 3D-dimensional meadows. So for the next few slides, I'm going to show the meadow we used here is so the shear density is 775 per meter squared. I'm sorry for the typo, but the original canopy height, so when there's no flow, is 14 centimeter. The water depth is 21 centimeter. So the meadow width is around 60 centimeter, and the channel width is about double the meadow width. And the open channel depth averaging flow velocity 5 centimeters per second. And when the blade bends, we use this deflected blade height, which is around 11 centimeters. Of course, it changes. Basically, it changes along the length of the meadow, right? But I mean, the average is 11 centimeters. So if we use that and put those into our analytical solution, so from our velocity measurements, we calculate the depth average flow velocity within the meadow. So right now for 3D-dimensional meadows, this is U1 3dx. And so on this slide, we plotted the measured U1 3dx against the analytical prediction. So again, triangles with arrow bars are the measured values, and the blue curves denote the model prediction. Again, so our model, so the measurement agreed really well with the prediction, such that our analytical solution is also validated in this case. All right, so next I want to talk a little bit about my field work. So again, so all I'm doing in the lab is really just trying to make this model general enough such that it could be used for the real world, right? Because the two-dimensional meadows almost never gonna occur in the real world, because in the real world, the Seagrass meadows, the size of the Seagrass meadows span a really wide range. So it could be just really sparsely it could be just sparsely transplanted a few shoots to like a continuous meadow of hundreds of meters long, right? But for most cases, it's three-dimensional, right? So, and what I want to do is I want to sort of to test our analytical solution in the field. So here on the left and the right, I show a kind of like a simple but nice method I developed to measure flow velocity in the field. So basically, you can see these two plastic blades bending in response to tidal currents, right? One is on a bare bed, basically a bare board with no vegetation, and the other is within a artificial meadow. And I mentioned earlier that the deflected height depends on flow velocity and blade properties. So from this deflected height that captured using the underwater cameras, we can infer and we can calculate what flow speed, what the flow speed should be, right? So I'm going to show some example here. So for this case, so the calculated flow velocity is 4.0 centimeters per second. And this is a GIF I made out of a 1-minute video. So just due to the instability, the blades are, just going up and down a little bit, but the mean deflection shows that the current should be around 4.0 centimeters per second. And this is more like this is the highest velocity I observed from these hundreds of videos I took underwater. So that's 25 centimeters per second. And that's when the tide changed directions. And this is like the maximum velocity in the other direction, which is 15 centimeters per second. All right, so okay, so by using this method, we can actually, just sort of test if our analytical solution that could predict the ratio of the velocity within the meadow to the open channel velocity works in the field. So on this slide, the predicted fully developed velocity was calculated from the estimated flow velocity in the open channel, which is the the blade you saw on the bare bed, the board with no vegetation. So and then we compare this predicted velocity with the measured velocity, and the measured velocity is basically inferred from the bending of the blade within the meadow. And so what we see here is that they agreed fairly well. So the blue line is the 1.1 ratio. And so even though it doesn't work as good as the lab results, but we still think that, we believe that this could also sort of validate our analytical solution in the field. So next, I want to talk about sediment deposition in the field, just to see. Wait, so let me show you this. Just start this video so you can see. So in this case, you can see like a lot of fine particles, a lot of sediment flowing past the artificial meadow, right? So what I did to sort of capture the short-term sedimentation is that I deploy a board underwater for about 1.5 months. And when I retrieve it at a low tide, so I can easily pick it up without losing any sediment, right? So, and then I measure the depth of sedimentation at different position. on the board. So what I end up getting is the image on the next slide. So basically we'll see here. So the tidal current is from left to right, from right to left, and the upper end denotes deeper water, shallow. So the lower end denotes shallow water. So what we can see here is that so the sedimentation near the edge of this board. So basically this plot shows the board, right? So you can see the sedimentation near the edges is significantly lower than that around the center, and that is exactly consistent with what our analytical solution suggested, that you have higher turbulence really close to the leading edge, and then in the fully developed region you have much lower turbulence, and you're going to expect higher sediment deposition, right? And to study this more sort of in a greater detail, or to look at a long-term sediment deposition, we did sediment coring in Hunt, Massachusetts. So we picked those different depth zones, which is marked by these red circles, and we take cores from from the leading edge of the meadow, and also we take cores at the center of the meadow. So we did that at different water depth, just to want to see to sort of better investigate the physical mechanisms that could impact sediment deposition in the field. So this is still a work in progress, and just due to this pandemic, we can't really. So there's no lab in United States that can help us do the isotopal analysis. So we want to do lab 210 to sort of measure the age of this sediment. So we know when we know the age of sediment at different depth in the core, so we know how fast the sediment is collected, right? So and then we can link that to the hydrodynamics, and just to see if we can correctly predict, like which spots will have higher sedimentation rates. And we can link that to the flow velocity and also the turbulence. But since it's still being analyzed at a lab overseas, so I guess we'll need to wait for this data. So, but I want to show you some data from the previous year, which is the summer 2019. So we did a much smaller scale sediment course. So we measured the percent organic matter in a 5 centimeter sediment course at multiple depth zones. So we find that it correlates with the shear density. So the upper panel shows the percent organic matter in the core in these 5 depth zones, and the lower panel shows the shear density. So basically what we see here is that where the shear density is higher, then you have a higher percent organic matter. And qualitatively, that is because when you have higher shear density, the flow velocity is reduced. Basically, the flow velocity reduction is greater, and you have lower flow velocity, and that will lead to lower turbulence. And lower turbulence will basically make more fine particles to deposit, and that would end up having a higher percent organic matter. But again, because we want to study this in greater detail, so and we're still waiting for the data. So back to the very beginning. So our study is trying to improve the assessment of these ecosystem services, and to provide guidelines for the seagrass restoration. and we want to understand the hydrodynamics. So right now we already have derived this analytical model for of flow development along two-dimensional meadows, and we have extended to three-dimensional and flexible meadows, and we also have extended to field conditions. I guess by now we just basically we can confidently say that our model has been validated and we can apply it to the real world. And there's a couple of applications I'm working on right now. So one is to improve the carbon batch estimation. Again, that's the data we are waiting for. We are hoping that by knowing this sedimentation rate at just different spot of this of the Seagrass meadow, and linking it to hydrodynamics and find a pattern, and we can hopefully predict the carbon stock for a whole Seagrass meadow. And then these theories can also be used to design artificial structures to protect transplanted seagrass. So the image on the right shows one of the ideas I was trying earlier this year, about maybe 1 or 2 months ago. So because I know how velocity develops, or how velocity evolves along these three-dimensional meadows, right? So and then and I know that the transplants, they like to live in low flow velocity and low turbulence environment. So I put these transplants in the middle of these two patch of artificial structures, which is basically PVC pipes. And we basically want, so which is kind of using these structures to protect the transplants, to hopefully make these transplants survive longer. And that's going to be a huge success for seagrass restoration. And that's pretty much everything that I'm going to talk about today. And for this Q&A session, meanwhile, I want to show a really interesting video that I found from my camera. What you can see is that actually 3 crabs were basically captured at the same time. Even though the artificial meadow is like really dense, but it's just really amazing that they can still like crawl inside and within this this sort of like a maze where, like, yeah. So yeah, so that's the end of my talk. Let me know if you have any questions. All right.
Okay, thanks, Gary. So like, thanks very much for the this interesting last video of 3 crabs. Maybe we can study the hydrodynamics of these crabs, like how to navigating in the your artificial meadow. But before we start this quest, maybe we should open the floor to to general public for whether they have questions. If you do, just raise your voice, since we are in the Zoom virtual way. So just raise your voice to ask question to Gary. So
yeah, I think you can also type in the chat. I think that also works.
So I guess I will start ask one question first. So I guess you haven't talked too much about a nutrition distribution inside these grass. And also you just talk about a one patch, let's say in a wild, I saw you that have 2 patch this to some degree tandemly this this artificial brick, artificial like a rod to like a protective this like transparent like a grass. So is there a way like think like this multiple patch or multiple meadow like being like arranged in an optimal way that like they can actually like to some degree interact with each other, so to like to harness the best like nutrition like for these like seagrass to grow, so in a way to like also like trying to sediment like to like to get like sediment settle. So
yeah, I think that's definitely something that is going to be really interesting to work on in the future, because so right now there are not that many or modeling or like those kind of things that could actually incorporate the factor, the impact of the three-dimensional meadows, right? So I think it's pretty, so the theory or the analytical solution of these three-dimensional meadows is very new. And if I can sort of collaborate with like a modeler, sort of, so basically for to put sort of my theory in this numerical simulation, then we can kind of predict any kind of flow development, right? For say what you mentioned, that different alignment or different layouts of multiple patches, right? So but right now I don't think there are any data out there that can actually lead this already. But I think that's definitely something I'm interested in working on in the future.
okay,
Yeah.
any questions from the audience?
Okay, I have a question.
Mm-hmm.
I saw that you showed us some data where the deposition in the meadow was higher than the deposition outside the meadow, but is that always the case? And do you have a way of sort of predicting when that might happen?
So yeah, so the deposition, I think in both cases is possible, and it all depends on the water depth, and it depends on the parameters I mentioned, right? I think yeah. I mean, we have this these experimental runs where the deposition within the meadow is actually lower than the reference, which is outside the meadow. So both are possible, and it depends on. I think it mainly depends on the water depth, which is basically the submerged ratio. So when I think when the meadow height is close to the water depth, then that case that's more likely to happen compared to a higher submerged ratio, which is when the height of the meadow is much lower than the water depth. Yeah.
So does that suggest that meadows that are deeper are going to be more likely to be good carbon sinks?
Yeah.
Okay, thank you.
Okay.
I have a question.
Yeah.
First of all, it was a very interesting study. I was wondering if you looked into or thought about the creating a type of meadow where the seagrass has a more realistic shape, in the sense that I imagine seagrass as having like a stem and then kind of like leaves on top.
Yeah.
And I was wondering if you thought about how, like probably at the top, at the edge, at the upper edge of the meadow, you would have like a higher density of mass, like with leaves taking a larger area. Have you thought of the implications of that on the shape of the velocity profile and turbulence at the edge of the meadow?
Yeah, so exactly. So actually, this is one of the case one of the experimental runs we did with the flexible meadows, and those plants look like real seagrass, right? And exactly as what you mentioned, so when it bends at the top of this metal, it basically it looks more dense, right? As compared to when it's upright, and that's definitely can be reflected. Basically, just so if you see the velocity profile of this case, you can see that the velocity actually is the lowest at the top of the metal. That's because exactly as what you mentioned. That's because
okay, I see.
It's the densest, right?
So the velocity profile within the meadow is not actually constant as you showed in that 2-layer model, but it's got
yeah.
It actually increases towards the bottom and then decreases again.
So from the back, it first increases and then it decreases because it decreases to the top of the metal and then it increases again.
Because the stems don't just bend like in the direction of the flow, but they also bend sideways. So they create a staggered mesh rather than a sorry, a non-staggered rather than a staggered one.
Mm-hmm.
Okay, yeah, thank you.
Okay, so I think like our time is almost running out. So let's first of all give a virtual like an applause to like a Zhang. So
thank you.
Thank you very much for your talk. So I see, first of all, I want to like do one comment. I see a lot of like mathematical derivation in like Zhang's like presentation. So it's a very beautiful like mathematics. Like we like fluid mechanics, we like mathematics. So, but like we need some time to like absorb. So there's a lot of there's Zhang's paper coming out. So if you're interested, like definitely go to see his paper. And by the way, his video will be like processed and later posted with his confirmation like online. Then you can rewatch with that. So with that, like thank you very much for Zhang's like time, and thank you very much for everybody to join. So like I'll see you next week, which will be 10 a.m. in the morning Wednesday instead of 3 p.m. in the afternoon. Thank you very much. Bye bye everyone. Stay safe, stay healthy.
Yeah, thank you. Bye.